Yeah, so I don't need to tell you that we've been going through an AI revolution in recent years. The most prominent example is probably ChatGPT. Can we remove this, or is it okay? Is that annoying? You can move it when they didn't do it. Okay. Yeah. As I said, ChatGPT is maybe one of the most prominent examples for this recent explosion in the capacities of AI. Other examples dating back about 10 years ago, developed by DeepMind, Google's DeepMind, the company that was acquired by Google, developed video games. Developed AI that beats some basic video games or beats human capacity in those games, and then finally also Go, maybe one of the most complex games that exist. The self-driving car. So when you go to San Francisco, you can use one of these to get around. They're called robo taxis. So there are no drivers, and it's a bit spooky to sit in them. But that exists already. So self-driving cars. But AI is really everywhere these days. Sales algorithms, and many more. But AI has also made inroads into science, and that was also already mentioned by Patrick. This example, Google's AlphaFold, which solved the so-called protein folding problem, so the problem of predicting protein structures, 3D structures from linear amino acid sequences. And that achievement also won the Nobel Prize in chemistry last year. DeepMind and Google has been pretty dominant also in science. So DeepMind has developed software that can predict or has predicted over nearly 400,000 new materials. We know about 20,000. And some of them have been confirmed already. AI has been used to increase the precision of gene editing. It has accelerated medical drug development. It's also been used in searches for physics beyond the standard model. And I'll get back to that example later. And it's also being combined with robotics to design self-driving laboratories. Okay. There's a question that is raised by this person here, Philip Ball, a well-known science journalist. And he's raised this question about AlphaFold. AlphaFold has not solved the problem. It says nothing about the mechanism of folding. The algorithm doesn't so much solve the protein folding problem as to evade it. How it reasons from sequence to structure remains a black box. So he seems to presuppose here that discovery requires something like an understanding of how AI generates the results. And this is directly relevant, so it's not just a philosophical point he's making, because the dynamics of folding also have repercussions for, or can have repercussions for the function of proteins. So yeah, he takes this more skeptical stance here, but the general issue that's at stake here is what exactly is really required for a scientific discovery in the first place. And that's the question I'm concerned with here. So here's a brief overview. So first of all, I want to introduce some broad principles of AI. I'm not quite sure what your backgrounds are, maybe a bit mixed. And then I'll give a very brief overview of where the recent philosophical literature has been. And then I'll turn over to an account of the nature of scientific discovery, one that I favor. And then I'll relate that back to AI. So that's more work in progress. And then I'll draw a conclusion and see what you'll say about it. So first of all, there are two broad classes of artificial intelligence. This more classic or symbolic approach also known as good old-fashioned artificial intelligence, was the main approach up until the early 2000s. And here the general idea is to represent the real world, or the problem that you're trying to solve, in terms of symbols and in terms of rules. So and the best example is maybe a chess computer, where you represent the figures in terms of symbols in your program, and then you have some rules that operates on these symbols. For example, the king can only move one square at a time. IBM developed in the 90s this computer that beat the world champion Kasparov. That was a big thing back then. I do remember that. But yeah, so this approach has limitations, and what people use these days mostly is machine learning. And one version of machine learning is based on artificial neural networks. And the principles, the basic principles of this approach have been known for almost as long as symbolic AI. But of course, things have, there's some new developments. For example, the complexity of these networks, but also high computing power. We shouldn't forget. For example, ChatGPT requires tens of thousands of GPUs, which is a more sophisticated version of a CPU that you have in your computer. So massive computing power is behind these things. Yeah, just to quickly explain the basic idea. So neural net is modeled on the brain that consists of neurons, which have connections to other neurons. So yeah, you actually call them artificial neurons. See these nodes in this network. They have connections that can be inhibitory or excitatory, just like in the brain. And then the signal is being propagated through this network. And computational science, they distinguish between different layers. So there's an input layer, output layer. That's not something that you have in the brain. And then most importantly, maybe these hidden layers between. And deep learning simply is the idea that there are several hundreds or tens, hundreds of thousands layers of these levels or layers between the input and the output layer. And I mentioned the development goes back quite a while, and in the beginning people started out with one layer. So the complexity has just risen, but that in itself is a model. So in the end, there's also computer code, of course. Okay. Yeah, and I should also say, yeah, there is, of course, the way that these signals are propagated is through action potentials in the brain, which have a threshold, and you can model that here as well with an activation function. And that sums the signals coming in from the other neurons. Okay. The three, so these networks are trained on data, and there are three broad approaches: supervised learning, unsupervised learning, and reinforcement learning. ChatGPT, for example, uses supervised learning mostly, also some of the other forms, but mostly supervised learning, where you present a network. So in supervised learning, you present a network with data, for example, here images of cats, and then you make the network recognize the cat as, so to say, and associate the image, with the output cat. So you presented thousands of pictures of cats, and you make this association. And supervised learning consists of the fact that there's explicit feedback to the network. For example, if the network mistakenly identifies a dog for a cat, then the network is penalized for that. Yeah, and in unsupervised learning, you don't have this explicit feedback, and reinforcement learning also involves some form of penalty or reward. An issue of these networks is opacity or intransparency. So even though we do know all the underlying principles here, we have difficulties figuring out what decisions the network makes on what basis for any particular input. So if the network has learned to associate cats with this label cat, what did I say? And then I want to know why this particular cat is being recognized as a cat. Then I will have trouble associating the particular weights that are attached to these connections with the particular input and the output. Okay. So that's so much for background. Apologies if that bored you. If you knew all that already. But yeah. So what is the current discussion in philosophy? Much focus has been on the opacity of AI in different shapes and forms. So one can distinguish broadly between ethical and epistemological concerns. And intransparency of decision making obviously is problematic. For example, in the medical context, if getting a diagnosis based on some AI computation, and you don't quite know on what basis the network or the algorithm generated this result. For example, you have a breast cancer, then you may be skeptical, or the justification may just not be so obvious. Recidivism is an interesting example. So in the USA, AI has been used to predict the likelihood of somebody committing a crime again once they've been released from prison. And there are these scores these programs that generate these scores, and they're actually being used in court as well when courts need to decide whether to extend a sentence, for example. But of course, the actual reasoning, as it were, is completely opaque to the ones affected, and that's an ethical issue, right? Because you don't know on what basis these decisions are exactly made. And there are also propriety issues, because the company that produces these algorithms, they're not very transparent about what they're putting into the program. But that's another issue. Okay, so that's one set of concerns. Another set of concerns are these epistemological concerns. Maybe not as the literature on these are not as extensive as for the first type of concerns. But here again, the focus is on opacity, and the question is, does opacity undermine our attempts to form knowledge about the world, roughly speaking? So I think that's more or less truthful for at least a number of contributions in this literature, this question. And what several philosophers have done here is they've called for nuance. So they've distinguished between different forms of transparency or opacity, and not all of them are equally problematic, maybe. And they have different implications, both with regards to the question of whether the use of AI is justified despite opaqueness, and also whether XAI, so explanatory artificial intelligence, is justified the use of that. And I want to diverge a little bit from this discussion, and I want to focus on the very notion of discovery. So in what follows, I want to give you an account of the nature of scientific discovery, and then come back to artificial intelligence afterwards. So what is a scientific discovery? What does it require? And if you look, for example, in today's standard work of philosophy, the standard Stanford Encyclopedia of Philosophy, there's an entry on scientific discovery, but the focus here is squarely on the discovery of ideas. And that's really where the focus has been, traditionally in the philosophy of science. It's a discussion that took place, I would say, in the 1980s mostly. So it's not really a topic that is so much discussed these days. And essential question has been, can there be a logic of scientific discovery? So is a logic, for example, to Newton deriving his laws of motion? How did he come up with these laws? How did he develop the theory, the idea? And this also relates to the two contexts of discovery, if you're familiar with that. Or sorry, the two contexts, the context of discovery, context of justification. And some philosophers have argued that the context of discovery is nothing that philosophers can say much about, and others disagree and say that that actually, there's a logic. For example, abduction is a candidate here. Of course, discovery in science also involves observations of objects, not just the development of ideas, but also the observation of objects. For example, discovery of the electron. But this you don't really find discussed here anywhere, and yeah, it's really, I would say, a neglected question, even though I would say it's quite central to discovery. Yeah, so how do we discover objects like the electron then? An obvious answer is, well, we detect and observe them. So whoever first observes the electron is the discoverer of the electron. For example, J.J. Thomson. He did these cathode ray experiments at the end of the 18th century, and so there's a cathode ray tube consisting of glass, and this tube you have to evacuate. So to produce a vacuum, you have a cathode and an anode, and you have a high voltage here, and then you get these cathode rays, which basically are just electrons. And he experimented with this, and then he decided at some point, or argued that what we actually have here are electrons. Yeah, interestingly, before Thomson was not the first to observe or to do experiment with cathode rays, so that they were known for decades, but people thought they were some form of light. For example, Hertz convinced himself of that. So obviously, it's not enough just to observe electrons, right? You look at the tube, and that's not enough. There's something more you need. Measurement, of course. But also you need to have some sort of conceptual understanding of there being electrons. And this is a view that has been defended by Thomas Kuhn. This is a view that I like a lot. And Kuhn develops this view in the Structure of Scientific Revolutions, obviously. And so this chapter 6, the anomaly and the emergence of scientific discoveries. And he argues that a scientific discovery doesn't only require that a new object is observed, but also an understanding of what has been observed. And he discusses the discovery of oxygen. Priestley or Scheele, so there was a Swedish chemist, Tikarian, I think. So there's a bit of a dispute who actually was the first observer, but one of those two first isolated the new gas, namely oxygen, but they didn't quite understand what they were discovering. So that was 1774. So Priestley identified it as common air first. And then he convinced himself that he actually had discovered dephlogisticated air. And that's, of course, surely not what he discovered, right? So dephlogisticated air, what does that mean? His theory was that when materials combust, they release phlogiston, and anything that's combustible has this principle phlogiston, and that's required for combustion processes. So equivalent to oxygen. And why did dephlogisticated air? So he thought that oxygen really was air that didn't have any phlogiston in it, and that made combustion processes, or that accelerated combustion process, because then the air could just, could take up more phlogiston, right? So that was the idea. And he believed that to the end of his life. So he never changed that view. And Kuhn argues here, well, Priestley was not the discoverer. We can't really say that because he also, obviously, we at some point we discovered what it was that we, what Priestley discovered, namely oxygen. And we need these both things. We need both the observation and the conceptual realization and what we discover. Interestingly, Kuhn implicitly requires some sort of correct understanding. Otherwise, we could just be happy to say that Priestley discovered dephlogisticated air in his paradigm, maybe, right? He doesn't say that. And that's interesting because obviously that's in conflict with some of his other views, for example, incommensurability. And my view on this is that we can just, ignore this and take Kuhn's account as it is presented here, and I think there are good reasons for that. And we can, isolate this account from the rest of what he says. You can also do that with normal science, I think, without having to buy into revolutionary paradigm changes. So I think Patrick disagrees with me here, but maybe we can talk about that later. An open question, though, is how correct must one's understanding be? I should also add, so Kuhn has this funny view about the discovery of oxygen, because obviously for him, Priestley is not the discoverer, and certainly not the only discoverer of oxygen. But Lavoisier, he's also a bit skeptical about him. So obviously he had some important contributions, but he also had some false beliefs. So first of all, he named the new gas. Oxygen goes back to him, the label or the name. And he understood that that new gas was important for combustion and so on, and had a mass. But he had some false belief about it too. So he believed that oxygen gas was the product of the principle of acidity, so equivalent or analogous to the principle of phlogiston. So in that sense, he was kind of still old school. And caloric, so the product of those two. And caloric, of course, also doesn't exist. Caloric is the substance of heat. That was also a popular view up until the, I think, early 19th century. So up until 1860, Kuhn argues that the view was abandoned then, and this conception that he had was also not given up until 1820. Yeah, but Kuhn doesn't want to say that oxygen was only discovered afterwards. So it was discovered before those dates, and so he ends up concluding that it was discovered sometime between 1774 and 1777, or shortly thereafter. So that's a bit dissatisfying, of course. So Hudson has argued that Kuhn left us with a quandary concerning how well one must conceptualize the discovered object in order for one to count as the discoverer of the object. And I should also say that so on Kuhn's view, again, neither Priestley nor Lavoisier are the discoverers. They both have a contribution, but we can't say just Priestley was the discoverer. He also argues that actually I'm not so much concerned with or bothered about identifying who's the discoverer. This is just a proxy for me to get a better understanding of what the discovery actually is. Okay, so Hudson comes out on the other side in a sense of this distinction. So he thinks that all you need for you to be discovered is some base description to successfully identify an object, a new object. And he does not even require accuracy of base descriptions. So for him, Priestley was just the discoverer of oxygen after all, because he was the first to isolate it, right? And his description of it was false, dephlogisticated air, but still he was the first one to isolate, and that's all you need. The problem with this account is that Priestley did not discover dephlogisticated air. So at some point we understood that what he discovered was oxygen. And Kuhn says nothing about, Hudson says nothing about that. And Lavoisier does not at all figure in Hudson's account, even though it's beyond dispute, I think, that Lavoisier had a very crucial contribution here to the discovery of oxygen. He himself, of course, made experiments, but his contribution was more on the conceptual side, I think, which was still important. Okay, so my view, just briefly, is this, that the discovery of new objects requires not only the observation of X, but also the correct conceptualization. So that's Kuhn, but then correct conceptualization of some of X's essential properties that suffice to individuate X. So what would that mean? For example, in the case of electron, would mean something like negative charge, particular mass, particular charge to mass ratio, wave and particle-like behavior, and so on. And what suffices to for you to become the discoverer is context dependent, depending on the context, the historical context, what is known at the time, that will determine to some extent how much you need, how much work you need to do in terms of identifying these essential properties. And of course, you don't have to identify all of them at one particular point in time. So it may well be that maybe there are still properties of electrons that we are not aware of, and that in the future we'll discover. But that wouldn't undermine a discovery claim made in the early 18th century, early 19th century, that discovery was, so that the electron was discovered. Okay, now I want to add to this this basic account a slight complication, and this is a distinction that Kuhn draws as well. So there are two types of scientific discovery, and he makes this distinction in the structure of scientific revolutions, but even more so in a paper that appeared at the same time in Science magazine, Historical Structure of Scientific Discovery, it's called. He does not talk at all about normal science, revolutions, or even incommensurability, which goes to show that you can really isolate this account from the rest of what he says. But yeah, so I would say the distinction gets slightly lost. It's still in structure, but it gets slightly lost, and a lot of people have overseen it, I think, or overlooked it. Yeah, and he doesn't give a name to these two types of discoveries, but I've called them that what and what that discoveries. Another label would be expected discovery. So in the expected discovery, you have an expectation, you have a concept, you form the concept of a theory, and then you go on to observe it. That would be a what that discovery. For example, Higgs boson, and I think, do I have an example? Yeah, in a second. So, and the other one is the type of discovery we just talked about, like the discovery of oxygen, where an object was discovered, it didn't really fit into the conceptual framework of the time, and then the framework was changed in order to make room for that new object. So it's actually, yeah, so this is wrong, because I made a mistake here. So that should be unexpected, and that should be expected discovery. Sorry about that. Yeah, so that's the label that I've used before, that what, because the thing is unexpected, and then you develop the concept for it, whereas here you have a concept or a theory, and then you observe exactly what you predicted. Yes. Expected discoveries are discoveries, again, for which scientists are prepared. They are associated with normal science, and Kuhn says about them that they're occasional for concrete relations not for a surprise. The Higgs discovery, I think, is a good example. So the Higgs was predicted in 1964 and observed in 2012. Right, so there's this long, as almost 50 years. So that's Higgs boson is a prediction of the Standard Model, also known as the God particle. I don't know if 2013, if you remember that, 20 or 12, when this was publicized, was massively in the press, and they liked to refer to it as a God particle. It's a particle that gives mass to the other particles. So this essential piece of the puzzle. And here's what some scientists have said about this at the time. Sean Carroll, it's a bittersweet victory when your theory turns out to be right, because it means on the one hand, you're right, that's nice, but on the other hand, you haven't learned anything new. It's surprising. Stephen Hawking, it's a pity in a way, because the great advances in physics have come from experiments that gave results we didn't expect. So this matches quite nicely this, this phrase, by Kuhn, occasionally for concretions, not surprise. But of course, it was a huge success and very important. So it's not to diminish the importance of it, but it simply was not something that wasn't expected. And moreover, physicists would have been happy maybe to get something that they didn't expect, because then they would have had grounds to develop new physics, because there's some limitations to the Standard Model. Okay. Unexpected discoveries. We saw this example before in oxygen. Kuhn also describes it as unanticipated novelty, surprising, and also troublesome. I won't go into that so much, but he thinks they're more troublesome also for the reason that we need to develop a new conceptual framework in order to make sense of them. So in that sense, at the very least, they're more troublesome. Okay. I don't know how much time I have left. It's 10 minutes or so. Okay, yeah. So coming back to AI. So with this framework, how do we categorize AI discovery? So in some sense, it seems to sit between these two types of discovery that I talked about. AI definitely seems to vastly expand and accelerate our predictive abilities. AlphaFold does an amazing job in predicting these protein structures. And we can also say that it predicts, of course, structures that we did not know before. That's why we're using it. I should also say that these predictions always have to be experimentally verified. So scientists don't just blindly trust this program. They use it as a kind of shortcut to get to these structures that they're interested in, and then they still verify them experimentally. But it's also true that there's no question about the identity of the objects that AlphaFold predicts in the proteins, right? So in that sense, they're not these unexpected types of discoveries where we do not know what we're getting, right? We know what we're getting when we're using AlphaFold. And this is not so surprising, given that AlphaFold, as I mentioned, uses supervised learning. Right? So you train the network on the basis of this, a lot of data where you have an association between amino acid sequences and protein structures. So AlphaFold was trained on this massive network of previous experimental work, right? So you know what the target is. You train the network to produce this target. And if you look at some of the literature on AI and science, then you find similar things. So papers that carry the title discovery actually are better described as rediscoveries. So, for example, it's been shown that you can extract heliocentricity of our solar system from simulated planetary data. You can extract Newton's law of gravitation from trajectory data, the time asymmetry of thermodynamic processes from molecular flow data. And in all of these cases, we know what the objects are that we're looking for, right? Or we know the right answers in a sense. But what about objects whose existence and identity we do not yet know about? And there's at least this one attempt from physics, as I mentioned. So there are these searches for what you may describe as known unknowns. So anomaly searches for physics beyond the standard model. So here's a depiction here. You can see the Higgs boson. So there are these it describes all the particles that we are aware of, quarks, gluons, bosons, and so on. But physicists know that this is not the final answer, because the model does not involve or incorporate gravity, dark matter, dark energy, and then there's also neutrino mass and oscillation. So that's been experimentally discovered or confirmed, but according to the standard model, neutrinos shouldn't have any mass. Yeah, and what have physicists done? So again, they were a bit frustrated in the early 2010s when the Higgs boson was discovered, not new physics, because they were hoping for something else. One alternative would have been supersymmetry theories, but yeah, that didn't pan out. But they're still looking for this new physics. So they have used unsupervised learning to try to find these new objects that could give us indication of new physics. And one way of doing that, one popular way, is to use so-called autoencoders, which are neural networks that consist of an encoder and decoder. And the encoder reduces the complexity of the data. So there's data on the mass, for example, and then the trajectories. So there are all kinds of dimensions to the data, momentum, and so the encoder reduces the complexity by focusing on the most important features that are, of course, defined by physicists, and then generates a compressed representation. So there's the input layer, and then there's this representation that they call latent space or latent space, and then the decoder reconstructs the original data. So yeah, so a specific form of a neural network. And the crux is that they train autoencoders on known physics, physics that they know, and then when the autoencoder encounters anomalous events, it will fail to reconstruct them. So that you get this error in the reconstruction, and that would be an indication that there's something new going on, and then that could be investigated. Okay, so there are two challenges about this. So first, detecting anomalies is not enough for discovery, according to Kuhn, right? We need to develop an understanding of what we discover. And that would require new concepts, applying them and so on. And AI by itself cannot do that, and probably it's not so clear it can ever do that, or will be able to do that. Even though some scientists believe that at some point there will be AI scientists. There's this Nobel Turing Challenge, which is often cited, which aims at developing AI scientists capable of autonomously carrying out research to make major scientific discoveries and win a Nobel Prize by 2050. We just witnessed Nobel Prize for an algorithm, development of an algorithm, but the idea here is that AI can do that by itself without any dependence on humans. So that's quite a tall order, I would say. But even if AI scientists are unrealistic, we still need some conceptualization, and maybe that is something that still humans need to provide. But of course, that by itself is maybe not a major issue. Another challenge, maybe more tricky though. So so there may be actually intrinsic obstacles. Even the first step may be detection of anomalies, right? So we need observation of something new and then the conceptualization. But the first step, there could be some intrinsic obstacles. So in traditional experiments, we need to distinguish signal from noise or confounders. So for example, when I want to measure gravitational acceleration, then I need to make sure that there's no air resistance, for example, right? Otherwise, the result will be distorted and incorrect. And the same, of course, we need to do also in these physics experiments. But there's because of opaqueness, we have a particular challenge here. So we don't know quite, we don't quite know, as I explained before, right? That's the whole issue of opaqueness, on what basis a network makes the decision it does make. And here's a funny example. So, so in this picture, AI may successfully identify or distinguish huskies from dogs on the basis of whether they appear in front of snow. So maybe huskies are more often associated with snow, appear more often in front of snow, right? And then we could quickly classify those two animals, but for very, strange and irrelevant reasons, in a sense. Right. So those are the features that AI would use to categorize this as a husky. So in physics, or in the search for new physics, that generates a particular challenge because, again, neural networks, they're opaque, but you also don't know the target, right? We don't know what the target is. We don't know what the new physics is. So here it's particularly challenging, it seems, or difficult to find out when an anomaly is detected. Is that actually an indication of a new object, or is that actually just the confounders, some noise produced by the machinery and so on? Yeah. So the end may detect, something as a signal, and when it's actually a confounder, and we wouldn't know. So that seems to be an intrinsic issue here, or obstacle to these kinds of searches. And yeah, again, compare this to the wolf-dog example, right? We know what a wolf is, what a dog is. We know what snows. We have these concepts, right? But here we don't. We don't know what the right concepts are. Okay. So if you're a little bit familiar with this, with AI, there has of course been recently, or have been these attempts to make these opaque methods more transparent, and this also goes under the label of explainable AI. And there are different approaches, but one important one are these post-hoc model unspecific approaches, where we try to explain why the model produces the output that it does produce. So, for example, there are these visualization methods where you can highlight that, for example, the AI or the algorithm would focus on the snow in this example instead of the dog. So there are ways of doing that. But there are also general criticisms of this approach. A much cited one is this by Rudin, where she's argued that XAI is potentially misleading and unreliable. So that was from a few years back, and a lot of research has happened since then. But this is still something people refer to. Yeah, and it's a bit curious that XAI has not been used much in physics at all. It seems. But there may be some reasons for that. So obviously the complexity is extremely high, resulting in very complex models, and also the data deluge is huge. So 60 terabytes per second they're processing, and this may make the use of XAI methods rather difficult. Okay, so this is where I get to my conclusion. So first of all, AI looks to massively expand our predictive capacities, and in combination with robotics may even expand our experimental capacities. If we think of self-driven labs, which people are developing. And Yet still, AI has to produce discoveries of new objects and relationships, I would say, in the sense of maybe not necessarily revolutionary discoveries, but certainly discoveries where the target is unknown and unexpected, and it's not quite clear whether that's actually possible because there are these intrinsic limitations to AI discovery. I would say again, it's a fact that many enterprise discoveries are actually rediscoveries. Programs like are much celebrated programs like AlphaFold are based mostly on supervised learning, where novelty isn't possible because you train a network to produce certain outputs. And even when unsupervised learning is used, like like at CERN in these physics approaches, you have this issue of signal noise discrimination, which is especially hard. So, in conclusion, the new AI gives us reason for both enthusiasm, I would say, because of the new possibilities and the uses you can put AI to, but there's also critical reflections on possible limits to be had. Okay, thank you.